EET 114, section 19.5. This is maximum power transfer theorem. The maximum power will be delivered to a load when the load impedance is the conjugate of the Thevenin impedance across its terminals. That is, for this figure, when ZL, the load impedance, equals Z Thevenin, that this is the magnitude, and when the phase angle of the load is equal to the I'm going to say the inverse of the phase angle of the Thevenin equivalent impedance, or in rectangular form, RL equals R Thevenin, which is what we learned last time. That's the resistive component, and then plus or minus J times the reactance of the load equals minus or plus. It's the polar opposite of J, of the reactance of the Thevenin impedance. So Z sub T equals Z Thevenin plus or minus J X Thevenin plus R Thevenin minus or plus J X Thevenin. Z sub T equals 2 times R Thevenin. Okay. So defining the conditions, the power factor is 1, and the maximum power equals E Thevenin squared divided by 4 times R Thevenin. That was the same formula as before. If the load resistance is adjustable, but the magnitude of the load reactance is not, then the maximum power that can be delivered to the load will occur when the load resistance is set to the following value. That's RL equals the square root of R Thevenin squared plus the quantity of X Thevenin plus X of the load squared. And the power delivered is then determined by E Thevenin squared divided by 4R average, where R average is R Thevenin plus RL divided by 2. There's also, we will not be covering substitution, reciprocity, or Millman's theorems.